received her master's from IIT Kharagpur and her PhD from JNU, and has since spent time in various places, including SACLE. And today she is going to talk to us about entanglement dynamics. So please take it away, Professor Shukla.
Can you see my slides? Can you hear me first of all?
Yes.
Can you hear me clearly, or should I use headphones?
No, I mean, I can hear you just fine.
Okay. And can you see my slides?
Yes.
And movement of the cursor?
Yes, all of the above.
Ah, great. Okay. So I'm going to start, but before I start, I must thank Arul for such a beautiful talk. I mean, I was just wondering how much time he must have spent preparing these slides and also presenting so beautifully. Anyway, let me thank the organizers also for providing me this opportunity to talk about my work. Today, I'm going to talk about entanglement dynamics of generic quantum states. And this is actually the continuation of the work which I had talked about in the previous same conference. And this work is done in collaboration with my student, Devanshu Shekhar, who is also here. And okay, so I'm going to skip my first two slides because already the conference this workshop is going on. So people must have talked about it. So I will skip this part and I'll start from here. So maximum entangled state, Arul has just talked about maximum entangled state. And let me just remove this. Yeah. And so question is, like he has already introduced, but let me just repeat it. What is a maximally entangled state? It actually corresponds to an equal a priori probability in all basis states such that the information, the knowledge of the state can provide about its subunits is minimum. As Arul also defined, actually what simply said that all the subunits of the system should be equally interacting with each other. And that means a given state which you are trying to find whether it is maximally entangled or not, it should access all basis states equally likely. That means it is ergodic. Okay, so that's what I mean. A maximally entangled state is expected by definition to be ergodic. The idea behind this comes from Berry's conjecture for quantum chaotic systems, later on improvised by Don Page in context of black hole physics. And the conjecture was a typical ergodic many-body eigenstate constitutes a random fork space vector with independently distributed Gaussian entries, which have also identically distributed. On the basis of that, Page predicted about the dynamics of the entanglement entropy of a state, but that dynamics only discussed in terms of the changing volume of the subsystems. So it said that the entanglement entropy approaches its maximum value exponentially as subsystem volume, system volume increases while subsystem volume remains less than half of the total volume. Okay. But now I'm going to talk about the dynamics, not only in context of changing system size, but also in other contexts. The question is why you need the information about the entanglement. Of course, all of you know why, but let me just repeat it. As we all know that for most industrial purposes, quantum computation or quantum information processes, we would like to avoid loss of information due to contact with environment. Okay. And this, of course, idealistically will require isolation of the system. But then the question comes whether you can apply the usual standard physics laws to isolated system, because can you apply those equilibrium statistics, equilibrium thermodynamics to such an isolated system? To avoid such questions, because still these questions are not completely answered. So there is another way that you allow the interaction with the environment, but hide the information in such a way that even if somebody, even if it comes into, the state comes into contact with the environment, the information is not lost. Okay, so that's what, that can happen actually if you distribute the information among as many subunits of the system as possible, and that also if equally likely. So that means ergodicity, again, concept of ergodicity comes here. So usually ergodicity is synonymous to maximum entanglement usually. Okay. Then comes the question, can a mini body state ever reach to ergodic state? Okay. So let me now, okay, let me, I'll come back to this question again, but let me first say other things. Growth of entanglement, because even if you prepare a state in the maximally entangled state, the system conditions are going to change for whatever reason. For example, in contact with the environment, and a typical state is expected to evolve in time, and it need not retain its initial entanglement situation. And entanglement measures in general tend to grow in time, because number of ways for a generic state to be entangled are far more than unentangled, because more entanglement corresponds to connection between more number of subunits, and naturally more number, than the moment number increases, you have more possibilities. Okay. Now this growth rate from a given, our typical state can also be system specific and can give a lot of information. Because it is system specific, it can provide a lot of information about the system. For example, many body physics and black hole physics, thermalization, and existence of a local conserved charge, etc. Okay. Then there are also people are interested about the bounds on the scrambling of quantum information. Although quantum dynamics is unitary, but still you cannot retrieve all the information, because ultimately, as I said, entanglement grows in time, and that means the information is distributed to more and more subunits if it is a mini body system. And then it's your own limitation of performing the measurements as the number of subunits increase that you cannot retrieve the information. So scrambling is basically the time beyond which quantum information cannot be retrieved completely due to our own inability, our own limitations. Okay. Okay. Because of all these reasons, it is necessary to understand dynamics of entanglement due to changing system conditions over time, because when we say entanglement is growing with respect to time, basically system conditions are changing over time. Okay. With this comes the question, which particular measure you would like to study for evolution, entanglement measure you would like to study its evolution with respect to time. Okay, because if you are studying the study of entanglement, evolution of entanglement, then you need to choose a particular measure and compare its value at various stages of the system conditions as they are changing. Okay, we all know that there are many measures to characterize the entanglement in a multipartite state. However, there is no unanimous agreement about among these various measures. Okay, for example, to say it more clearly, the relative degree of entanglement between two states indicated by one measure differs from other. Okay, that is certainly true in case of multipartite state, and that is a holy grail of multipartite entanglement. Okay, but it was previously believed that such an issue does not arise in bipartite system, and this belief was based on systems without conservation laws or disorder. And the studies on these systems indicated that the standard entanglement measures, that means information entropies, namely Von-Neumann and Renyi entropy, show a linear growth. Okay. However, this is no longer the case, because recent studies have shown that growth rates in time of, time-dependent growth rates or growth in time of Renyi and Von-Neumann entropies differ. if the system is subjected to physical constraints. And that's a real situation, because almost all real systems are subjected to physical constraints, some or the other. What kind of constraints we are talking? Global constraints, for example, symmetry or conservation laws, etc., or local ones, for example, disorder, dimensionality, etc. I'll come back to this again later. Then another observation based on recent study is that the Renyi entropy has slower growth than Von-Neumann entropy. Okay, and most of the evolution of entropies are questions coming from the black hole physics. Okay, not only the growth growth is system dependent, and growth is also measure dependent, but maximum growth is also system dependent. For example, based on page prediction, the expectation would be that typical many-body eigenstate at high temperature are maximally entangled. But actually, experimentally, it was found that the eigenstates of translationally invariant fermionic Hamiltonians violate the prediction. Okay, so now comes, what are the questions actually, or what are the questions we have focused on? Role of physical constraints on the entanglement growth, how the entanglement is affected by system conditions. Then second question comes, is it sufficient to know the average values of entanglement? Because in almost all the papers, they will be discussing about the average Renyi entropy, average Von-Neumann entropy. Do these entanglement measure fluctuate? And if it has any relevance in context of quantum information. Then the third question, of course, was the question Arul also referred to in another form in his talk. Starting from a state with arbitrary entanglement, can a controlled variation of system parameters lead to maximum or desired entropy of entanglement? Okay, so these are the questions I will be focusing in this talk. But before that, let me just, I don't know how much review work has been done in this conference, in this workshop. So let me just quickly go through a little bit of revision. We all know that entanglement state can be pure or mixed. A pure state can be written in the projection operator. This is a density operator. I will really go quickly through this. A mixed quantum state is basically a probabilistic mixture of pure states, and can be, the density operator can be written in this, where pk is the classical probability. And there are two simple tests to determine whether rho is pure state or not. Rho is a pure state or mixed state. If the square of the density operator is equal to rho itself, then it is a pure state. If not, then it is a mixed state. And then another measure is to calculate the purity. Because I'll be using purity, so it's good to good to talk about it just now. A purity is defined as trace of rho square, and for a pure state it is 1, and for an impure state, that means mixed state, it is less than 1. Okay. Now let's just look at the real many-body state so as to know the complexity of these problems. As you know, a typical state of G particles written in n-dimensional single particle basis is of this form. So these phi p1 denotes the is the eigenstate of the first particle, and each particle can be in n states. Similarly, second particle, similarly G particle. For simplicity, I'm taking all these particles having the same number of states. In general, they can have different number of states, eigenstates. So different number of relevant eigenstates, that's what I mean. So basically, as you can see, the number of coefficients to write the typical state in a product basis of single particle states will be n to the power g if each single particle state is of dimension n. Single particle basis state is of the dimension n. Okay, so now for simplicity, again, consider g is equal to 2. That means there are only 2 particles. So naturally, number of coefficients will be n square. You can arrange these coefficients in a vector form. That means C11, C12, where 11 is how the 11 tells you what is the correlation between, what is the coefficient, what is the correlation between the first state of one system to the first state of another system. And similarly, okay, you can either organize them in the vector form or in the matrix form. Naturally, matrix form is more convenient because it is n cross n, number of coefficients are n squared, so you can arrange it. However, in the context of when you have to deal with n to the power g, it leads to gth order tensor, and that's how to handle it. I think Arul has already introduced it to a certain extent. Okay, so I'll quickly go through this. Okay, now comes the, okay, but I'll not be talking about multipartite entanglement. I'm going to talk about the very simple, very well-studied case. However, the new results about this, which have not been talked about so far, the bipartite entanglement of a pure state and its evolution with respect to changing system conditions. So let me now, so I'm talking about G is equal to 2 only, and the coefficient matrix therefore is a coefficient, these coefficients can be written in a matrix form, n cross n matrix form. Okay. So basically I'm talking about, let's consider a system divided into two partitions, A and B. And for simplicity, we just take each, for schematic presentation, I just take force. So it's a many body system of 8, let's say, qubits. However, to consider as bipartite entanglement, I just put 4 units in one part and 4 units in another part. And so part A and part B are entangling, are interacting with each other, and I'm interested in how they are interacting with each other. Okay, these 4 states can also, of the subsystem A, partition A, can also be written in the Q form, in hyper Q form, and then these C coefficients denote how the basis, how the states of system A are interacting with the states of system B, and therefore we are not talking about the interaction within a subsystem, but interaction across the 2 subsystems. So that's what coefficients are just talking about, the interaction between 2 subsystems, not within the subsystem. Okay, as we all know that the for bipartite analysis, it's better to study reduced density matrix. So reduced density matrix corresponding to subsystem A can be found by integrating over all information about the states of subsystem B. So it is written mathematically in the form of trace of B rho, and you can just you can substitute, rho is this for pure state as we are talking about. So it can be finally reduced to CC dagger, where C is a matrix which contains these coefficients as the matrix elements. As most of us know that CC dagger is a Wishart matrix, a typical Wishart matrix. Okay, and C matrix is in general rectangular, NA cross NB if A and B of size NA, if A is of size NA and B is of size NB. For example, in the this schematic picture, A is of size 4 and B is size of 4. So it will be a C is matrix 4 by 4 matrix. Okay. Now quickly the entropy of entanglement. I'm going to focus only on 2, although it can be generalized to many more, our work. So we are talking about the Von-Neumann entropy, which can be written as minus of trace of rho A log rho A. Rho A was a reduced density matrix, and R2 is the Renyi entropy, second Renyi entropy, and can be written as minus log of trace of rho A square. Now, as you see, in both cases, trace is appearing, and therefore trace of rho A. So that means trace of a matrix can be written in terms of the eigenvalues. So naturally, these 2 entropies can be written in terms of the eigenvalues of the matrix rho A. And let us remind, rho A was a Wishart matrix. So basically, the problem boils down to study the eigenvalues of a typical Wishart matrix. Okay. So first question is, write down the reduced density matrix corresponding to your bipartite system, and then calculate its eigenvalues for by whatever means. But comes the question, is that enough? How about the typical state of a complex system? Okay, is that enough to just write down a reduced density matrix and its eigenvalues? So let's first look what happens in the case of a complex system. Okay, no, before that, so I have another slide to show. what does it mean, typical state of a complex system? Because often we just keep talking about maximally entangled state, but let's take a look at a typical state of a system, not even a complex system. So typical state actually typical bipartite state, of course. So these are, suppose, the states of partition A, these are states of partition B. So in a maximally entangled state, of course, each state is interacting with the state of other partition by the same, the correlation is same. That means strength of interaction is same. Okay, so that's what here is, it is denoted by 1, 1, 1. And similarly, A2 will interact with all the B states in the same way, 1, 1, 1. So this is a maximally entangled state, or uniform correlations among these partitions. Okay. However, that need not be the case, because as we know, when we look at the states, that need not be always the case. Actually, typical state will never be like that. So, and even if it is in some condition, it is like that, it will change because of the perturbations to the system. So, for example, even if the first state of A is interacting with the first state of B by correlation is 1, but the first state of A may not interact with the second state of B by the same way, and it can be different. So you can have this situation that although the interaction between the first states of A and B is same, but first state of A does not interact with other states of B in the same way, but they are same after that. Okay, 1B, 1B, 1 by B, that means the interaction is same of first state of A with other states of B except the first state of B. Okay. Similarly, you can have many other situations. I'm just giving the schematic picture of 4 situations because I'm going to use it for my numerical analysis later. Okay. So other state is power law. For example, you can have the power law variation of the interaction between various states of the 2 partitions, and or exponential also. Correlations can change exponentially also, increasing, decaying, all kind of varieties are possible. Okay, but this is for any generic system need not complex. Okay, need not be complex. Let us see what happens if you are dealing with a complex system. Question is, of course, the basic question is, when you write down a generic many body state in a let's say product basis of single particle states, because that is the most suitable basis, because if you want to study how the interactions of the many body state, because all the physical properties of the many body state depends on its nature of interactions, and if you want to know how these interactions are changing, the best basis is to choose the product basis, in which the basis is when there was no interactions, and now then you can really see how the interactions are changing the scenario. Okay, so the question is, however, if you are dealing with a many body state, can you really calculate the coefficients in the product basis? Why this question comes? Because your system, many body system, is having many complicated interactions. Even if these interactions are like Coulomb interactions, like electrons, there comes the question that you have to write down the Hamilton, you have to work out the Hamiltonian in some matrix form in the basis, in the product basis, and you have to calculate the matrix elements. For matrix elements, you have to calculate the integrals. Because of the complicated interactions, you can write down the integral even if you know the interactions exactly, but you will not be able to calculate these integrals exactly all the time for all the situations. Okay, so that's what I say, that the lack of detailed knowledge about complicated interactions between subunits manifests itself by randomization. Randomization can be partial or full of various operators. Of course, let's just talk about Hamiltonian in this talk. So, and if the Hamiltonian is random, partially or fully, because why partial? Because some integrals you can exactly work out. Some matrix elements you may be able to work out exactly. but some you may not, because somewhere interactions may be weak or maybe very well defined or maybe much easy to solve the integral, but in some other parts may not. So Hamiltonian can be partially or fully random. And of course, because the Hamiltonian, you have to calculate, you write down the typical state of this Hamiltonian by calculating its eigenfunctions. If the Hamiltonian is random, eigenstates will also carry that randomness. That randomness will also manifest in the eigenstate and thereby any typical state of the system. Okay, so some or all eigenfunction components of a typical state can be random. Okay, and if you are talking about a bipartite state written in this basis, then C are the coefficients. That means C are the eigenfunction components in this basis. Then C can be random. That means the matrix C is random, and therefore our Wishart matrix of the reduced density matrix is also random. However, you often hear the people talking about stationary Wishart matrix, where all matrix elements are taken of the same order. Okay, even if they are chosen as Gaussian random, but they are taken of the same identically and independently distributed Wishart matrix elements. But that is not true because for the simple reason that, as I gave you by a schematic picture previously, that theseCijs can be of various shapes and sizes. For example, I showed you here in this picture, these arrows, the number mentioned on the arrows is actually Cij, because this is C11, this is C12. So they can all vary. They need not take the same value. Okay. And in the case of a random matrix, of course, you cannot write down the precise value, but then you talk about the variance, the distribution, even they need not have same distribution. Okay, so the question is, how do you determine the distribution of C matrix if a complex system, if you don't even know? So comes the, but before I talk about that, I just say what happens if the, your matrix C is random. Then, of course, the Wishart matrix is random and eigenvalues are random. And then this is the Von-Neumann entropy in terms of the eigenvalues of the C matrix. This is a Renyi entropy in terms of the eigenvalues of the C matrix again. If C is random, its eigenvalues lambda n's are random. That leads to randomness of R1 and R2. Okay, so if you write down the distribution of eigenvalues of the reduced density matrix or Wishart matrix as P lambda, and there are n eigenvalues, then you can calculate the distribution of R1, or rather probability density of R1 by using this mathematical definition. This is just defining R1 in terms of the Schmidt eigenvalues. The Schmidt eigenvalues are the eigenvalues of the reduced density matrix, and this is just the condition that trace of density operator should be 1. Okay, so similarly, you can write down for the Renyi entropy also. Now, this is the condition for defining the Renyi entropy, and this is the constraint because of that trace of rho is 1. Okay, values of the C dagger matrix. Okay, now C dagger matrix. So in order to know the eigenvalue distribution of C dagger, you first have to determine C. What is C? There comes a question. So to say this question, repeating, what is the probability density of C matrix under the criteria that it does not carry any more information than that is provided by the constraint? So here comes the maximum entropy hypothesis, which says that what you should do, write down, we are not talking about the Von-Neumann or Renyi entropy now. Another entropy enters the picture, Shannon entropy, the classical entropy. And maximum entropy hypothesis says that you write down the Shannon entropy and whatever constraints you know, use them as a Lagrange multiplier and maximize entropy, and find the solution which maximizes the entropy, Shannon entropy. Okay. So if you know the constraints, for example, in the moments form, so distribution can be determined using maximum entropy hypothesis, and available information puts constraints on the moments, or available information puts constraints on the distribution. Now, again, I come back to, because what people observed in context of black hole physics, that the constraints affect nature of entanglement measure. So question, how constraints are affecting our C matrix? And we are dealing with a complex system. So C matrix is represented by an ensemble, or okay. So what are the, so nature of the ensemble depends on global and local constraints. Okay. Global constraints are those which are applied on the system as a whole. So for example, a single matrix is subjected to those constraints. For example, the conservation laws of symmetry. And local constraints are those which are not, I mean, which are only affecting the locally. That means they can lead to, they are not affecting the, if you are representing the system by an ensemble, then they can only change the ensemble parameters, distribution parameters, for example, in presence of disorder or dimensionality that can affect the distribution parameters. I will not talk much in detail about this. That is, these are just two types of main constraints. Okay, although sometimes it is not so easy to differentiate between global and local, for example, in case of dimensionality. Okay, but this is not really this idea does not is required for this present talk, and therefore I'll not talk more about it. So to understand the leftover talk of mine, let me just remind what maximum entropy hypothesis says about the case when you have only the first two moments available. That means you know that the matrix element, the variance of the matrix element is given by 1/2 gamma, and the mean value is 0. Okay, so that means here you are talking about a bipartite state where all coefficients, although you cannot determine them exactly, but whatever uncertainty you know about all the interactions between orthogonal bases of states of system A and B, the same uncertainty is there. Uncertainty does not vary. So equal a likely probability, and their mean is 0. So if you maximize this information, apply the maximum entropy hypothesis, it leads to distribution of C matrix in this form. Of course, I have eaten the constant, but that is not needed for our discussion right now. And of course, it can be written in the form of reduced density matrix of trace of A. Okay, so if you remember, this is also the form of the stationary Wishart matrix. Okay, and we all know that the stationary Wishart matrix corresponds to maximum information. The standard Wishart matrix gives rise to maximum entropy of entanglement. Okay, Von-Neumann entropy of entanglement or Renyi entropy of entanglement. So that means we started with this, started from here using the maximization of the Shannon entropy. It leads to maximization of the Von-Neumann entropy. Okay, so this is how we use the maximum entropy hypothesis to write down the case of maximum entanglement, maximally entangled state or ergodic state, because that all variances are of the same size is actually, that means all basis states are interacting with each other in the same way, and that corresponds to an ergodic state. Okay, so this is exactly I've already said. So let me keep moving because my time is coming to an end. But the question is, this is not really true. We can immediately see why should all states be interacting in a typical state. All states of A and B should be interacting with each other in the same way. Of course, it should vary. Okay, so So a typical many-body state need not be ergodic. Not all matrix elements of C are of the same order. This is the most general form I'm writing, and this is the constraint you impose. Now, if you apply constraints only on the first and second moment of CKL, like you did in the previous case for the maximally entangled state, then of course, now you are changing. Although you are still applying constraints only in the first and second moment, but these are no longer same. So a more next level generalization of the state will be, what you just saw, will be that all the variances are different and the mean values are also different. So this is, note, previously we had taken all gamma KL equal. Okay, and that's why it becomes very easy, and BKL 0. But now I'm no longer talking about that. Of course, FC is the same condition, trace rho is equal to 1. And also, if there are other conditions on the system, then FC will include other conditions. And is the normalization constant. And okay, I don't know why I've written here, but that may be, okay. This is not really entering here. Okay. Of course, if you know more constraints on higher order moments, which apply constraints on higher order moments of matrix elements, it will lead to non-Gaussian ensembles of constant matrix. So what I'm trying to say right here, a typical state is not represented by a stationary Wishart ensemble. Okay, and you have to study, because if C is of this form, then naturally it will lead to Wishart matrix in a much more complicated form. Okay. So, for example, this is a schematic picture. You have, because I have to show it to you because I'm going to use this for my numerics. Okay, this is a case for stationary Wishart ensemble of the C matrix representation. The color coding here is such that if the same color is there, that means all matrix elements are statistically same. So here, all matrix elements are shown by red color. So that means all matrix elements are statistically of the same strength. So that means that represents the ergodic state, because each matrix element corresponds to the interaction between a given state of A and another state of B. And all these interactions are correlations or interactions, whatever you prefer to call, are same. Okay. However, here there is a different scenario. Here, only first column is of the same color. The other columns are for different color. So first column tells you how the first state of A is interacting with all other states of B. So first state of A is interacting with all other states in the same way, but the second state of A, third state of A, fourth state of A is not interacting with other states in the same way as the first state is interacting, but otherwise they are same. You can further generalize it. Here the color coding is, of course, color is changing all along, but here if you look at the visible spectrum, taking the color of the visible spectrum, here color is changing softly. So there is a soft change of the correlations between two orthogonal basis of partitions A and B. Here there is a drastic change because color is changing rapidly. So this I call exponential change. I will give you later on the, hopefully, if I've included it. Okay, so here is, I'm considering the exponential decay variation of the correlations between A and B, and here I'm considering only power law decay. Okay, but that is numerics, that comes later. Let me see how much time I have. I think I have only 20 minutes left. Let me just go quickly. Okay. So basically comes question, I said that a most typical state, of course, will have much more complicated, but let us just consider for the time being this ensemble here, that your C matrix is represented by this ensemble. As you see, there are so many parameters entering. Is putting the variance of each matrix element, and BKL is a mean value. There are so many parameters, of course, variation of A, and all these distribution parameters, variances and mean, contain information about the system parameters. And as system parameters change, these distribution parameters change, and so does the ensemble. Okay, the question is, when these parameters are changing, there are so many parameters, how long can you just keep on tracking the variation of one or the other parameter? Is it possible to describe the variation of any of these parameters or all of these parameters in a universal, by a single parameter? The answer is yes. and I will not get into detail. Actually, you can describe, if you change any of or all of or some subset of these parameters, the ensemble density of C matrix evolves by this diffusion equation, which is, and this is because of the Gaussian nature of this distribution, where this parameter y is basically contains information about all these distribution parameters. Look, HKL variance is entering here and the mean is entering here. And what I want you to note is the appearance of log, because I will come back to this in the end. So similar to like log is entering everywhere in this case. So log is entering here again in the parameter, which is actually governing the evolution when you change the system parameters. This equation does not, nowhere HKL and BKL are appearing in this equation, only Y is appearing, and Y contains information about all the system parameters. So it's some kind of average. It's some averages out and does not care whether how HKL or BKL are changing individually, but only if Y changes, then this evolution occurs in the ensemble density. Okay. Now this, as you see that if all HKL are equal and BKL are 0, it will be the stationary Wishart ensemble, which corresponds to maximal entangled state. So that's what I say. That corresponds to, you can substitute HKL is equal to same and BKL is equal to 0. It leads to Y goes to infinity. And so in Y goes to infinity limit, it is a stationary Wishart ensemble. That means maximum entropy ensemble. Okay. So now the question is, but how do you calculate the distribution of eigenvalues here? Because if you can calculate the distribution of eigenvalues from here, you can calculate the distribution of Renyi and Von-Neumann entropy. Okay, so you can show that this is the, if you can calculate by exact diagonalization of this matrix diffusion equation in the matrix space. If you exactly diagonalize, you get the diffusion equation of the density of eigenvalues in the eigenvalue space. And this is the equation turns out to be. And I think I have mentioned it in the next slide, that if you put this side is equal to 0, because Y goes to infinity, this will go to steady state, then the solution of this is basically stationary Wishart ensemble. So when Y goes to infinity, this equation also says that it goes to maximally entangled state P lambda. When Y goes to infinity, the distribution of Schmidt eigenvalues goes to the corresponding to that in the maximally entangled state. Okay, so but what about the general Y? Because that is what our typical state we are interested. A typical state does not correspond to infinite Y, because typical state corresponds to finite values of these HKL and BKL, and they can take any values. So what is the solution of this equation? Because if you know the solution of this equation, you can calculate the Von-Neumann and Renyi entropy distribution. Okay, so I am interested in studying the distribution of Von-Neumann entropy and Renyi entropy for a finite value of Y, not only maximally entangled state. This is what I have written, that I have already said. So because my time is running, so I'll quickly move. You can identify this is a solution which you know is of the stationary Wishart ensemble. I think there is a mistake here. It should be square here. So, okay, let me, I have already shown you. So I'm now interested in distribution of Von-Neumann entropy as a function of Y. Okay, because Y contains this information about the system conditions. If I can solve, I will know for a given system condition, I will know what is the distribution of Von-Neumann entropy. So this is the formula which I have already showed you, and I don't have time, so I'll just flash the equation. The distribution of Von-Neumann entropy can be given by this equation. Okay, turns out to be. This is a non-linear equation because these parameters delta, which is now appearing, is the mean level density, which by itself depends on the parameter y, and therefore it's not easy to solve this equation, but it can be solved for large y. And it okay. Now here again I'm showing, but because I think next slide is, yeah, I'm showing the numerics. So this I've already talked about, that this corresponds to equal correlation between matrix subsystems, and this corresponds to only first state is correlation between first states of two systems are same, but others are different, and this is different as a power law. This one is different as a exponential. Okay, so let me now quickly go. So here is a result, because I cannot justify my theoretical, so I'll now focus, because I have only, I think, 10 minutes left. So I will focus now on numerics, and this numerics is all done by my other student Devanshu, who is here. So here I show the three cases. This is the where I will call it constant ensemble, not constantly uniform. It's not uniform, but it's constant. I just, for simplicity, I refer it as constant. This power law, this one, and this is exponential decay of correlations. Okay. So you see, for the constant variance among higher columns, this is the distribution of Von-Neumann entropy shown for three different values of y. This is for y very small. Y is almost touching 0. This is y almost is much greater than 1. Devanshu can correct me if that is wrong, but y is much greater than 1. But this one is y of the order of 10 to the power -4. That means it is y is not very far from 0. But you see, although this one, and I think you cannot see the numbers, but here the width of the distribution is very small, and this is also a log normal distribution, while here width has increased. And so width is now, and it is a Gaussian distribution. And as y increases, it again goes back to log normal distribution. So from log normal to Gaussian to log normal, and as y increases, because y is equal to 0 corresponds to product basis, because y, okay, so it's a separable state, and y very large corresponds to maximum entropy state, because as I already said, that maximum entanglement state, y goes to infinity, goes to maximum entropy state. That corresponds to maximum entangle. So y is equal to 0 to y goes to infinity. In between, you see the distribution of Von-Neumann entropy is not negligible. Okay. Similarly, you can look at another typical state represented by another ensemble, power law decay. Again, you see. Okay. And when you cannot see the numbers, but if you see that they are all having the same width in the intermediate case. Okay. So distribution seems to be independent of the system details. That means same for all three ensembles. How? Okay, so here are the inferences before. Okay, I still have some time. So log normal, I think I already said, log normal distribution of Von-Neumann entropy distribution of R1 for y is equal to 0 and large y. Gaussian distribution for y approximately 10 to the power -4. Width and mean almost same for the three cases. Three cases means three systems, three different ensembles. Details of the ensemble irrelevant, only y relevant. That means it does not depend on the explicit details of H and B, because if it depended on H and B were different in these three cases, because in one case it was power law, other case it was exponential, in this case this was constant. So they should have looked different, but they don't look different, at least appearance wise. So therefore, but as you vary y, they go from one end to the other. So y matters, but not the individual explicit details of the system conditions. Okay. Now, the one main thing is fluctuations of R1, which I did not see so far. Many people have considered fluctuations of Von-Neumann entropy around its average cannot be neglected. And that has implication for ordering the states in increasing entanglement using R1 as criteria, because if two neighboring states fall within fluctuation range, then you don't know which one you can call as increasing entanglement or same entanglement. Okay, distribution is also size dependent, distribution is also symmetry dependent. You can also study distribution of purity, same way, and I don't have time. Again, you find the same 3 cases I study, you find that as y varies, the density, probability density of the purity changes from one into the other, from separable to the entangled, and again log normal, and it is normal. I think I think I said something wrong. It went from log normal to normal to normal. Not the y goes to infinity limit. It is not log normal. It is normal. Similarly here, this again goes from log normal to normal to normal. This is increasing y. But as you can see, the details of the ensembles, that means whether it is constant or power law or exponential, shown by these 3 pictures, seems to be irrelevant, because I can see that even the width seems to be same. Okay. By the way, we are still doing this work. So this work is still going on. So, okay. Now, you can now ask, what is the average growth of von-Neumann entropy? Okay. So now, how do you calculate the average? You have already worked out the y dependence of the probability density of R1. And from here, this is just if you know the probability density of a variable, you just calculate the average like by using this standard formula. Now, but if the probability density of R1 depends on y, you can ask how average value of R1 changes with y. You can work out, this turns out to be of this form equation, and you can solve with this equation, standard solutions, it is of this form, but I will just show you. You see that in general, it depends on, the parameter nu and the parameter beta. Parameter beta tells about whether the matrix C is, you are taking real matrix or complex matrix. Real matrix will happen if you are taking, if your system has time reversal symmetry, because time reversal symmetric state can always be written in the can always be written in the product basis with real coefficients. And nu is basically tells you the size of, nu is a measure of the relative size of 2 subsystems, because both nu and beta are appearing in this general solution with for finite y. So the average value of von-Neumann entropy for a typical state, for a many body system or for a complex system with complexity defined by parameter y, depends on both symmetry conditions as well as the relative system size, okay, of 2 subsystems. Large y limit, again, it goes to constant, but large y limit is the maximally entangled state, and that we already know what it should be. But now you see, it is not going to a stationary Wishart ensemble limit, because nu is again entering here, although beta is not entering. The maximally entangled state does not seem to depend here on the symmetry parameter. Okay. Similarly, you can consider the growth of second Renyi entropy, and again, and you can calculate second. And here now I'm showing for the 3 ensemble study the comparison of average von-Neumann entropy and average Renyi entropy. And you see, I think blue is the top curve is von-Neumann, and the lower curve is Renyi entropy, and inset shows for small y values. So this is a plot of 2 entropies with respect to complexity parameter y. I call y as the complexity parameter because it contains information about all the system details. So it's some sort of measure of the complexity of the system. So you see in the inset, they are remarkably different from each other. They are not same. Okay, but they are all growing in the same way. Okay, although this is for the first ensemble, this is for the power law ensemble, this is for the exponential ensemble. So you see, for the constant, it rapidly decays, rapidly changes. However, here there is a smooth change from first it is increasing linearly, and then it suddenly becomes smoothly becomes constant. While here it increases linearly, but then it suddenly changes to a constant value. Similarly here, it changes smoothly from linear behavior to constant behavior, but all the time Renyi entropy is less than the Von-Neumann entropy. Okay, and how much it is less depends on the system details. Note, the same system detail did not enter in the distribution, because I showed you the distribution looked almost the same. But here, the average value does depend on the system details because the behavior is different. Look here, behavior is different. Okay. But as I said, this work is still going on. And I think this is also because Devanshu has not studied the distributions at this value, because I'm sure if he studies the distribution at this value, he will find the difference. By the way, I'm actually giving this talk from ICTP, and I'm not in, I'm far away from Devanshu. That's why I could not ask him to continue, carry out this calculations before presenting this talk. So, okay. So what are the inferences here? Let me see how much time. Oh, I have run out my time. I have already said all this. So let me just quickly go to my conclusion. You can also study the size dependence. There is a size dependence of the average entropy, which is displayed here. Now let me just quickly come back to my conclusion. Maximum growth of entanglement is restricted by conservation law. Entanglement does not grow to the maximum value that of an ergodic state. It is subjected to the constraint that is conserved from the initial state. Maximum entanglement can be achieved by variation of the complexity parameter y goes to infinity. It does go to the maximum entanglement. Okay, allowed by the constraints. For finite y, it seems almost same distribution for different ensembles, but rate of change of average entropy is different. I'm not 100% sure about this conclusion. But what I'm 100% sure about is fluctuations of entanglement measures relevant for typical states, noticeable even at y is equal to 10 to the power minus 4, which seems to be very close to 0, although their average changes at y of the order of 1. Now, what I want to indicate most sharply is y has a form of an information theoretical function. It is a sum over logarithmic values of the uncertainties associated, because look, it depended on variances. So it is a sum over logarithmic values of the uncertainties associated with pairwise correlations of the basis states. Uncertainty HKL associated with CKL. But what is CKL? Defines the pairwise correlation of the basis of the orthogonal basis of A and B. So it is a measure of total information content, also called surprise or self-information or basis state correlation. So should it surprise us that one information content measure is describing the evolution of entanglement measure statistically? That's it. Thank you very much. Yeah.
Thank you very much, Professor Shukla. Are there any questions? We still have a little bit of time because we are officially, I think, in the lunch session.
Sai Arul here.
Yes, please, Arul, go ahead.
Yeah, thanks. Thanks, Pragya, for an interesting talk. My first question is to do with the average size, dependence, which you mentioned in the end. So for the page formula, it's like for large dimensionality, log of the dimensionality minus half, or typically D. So largely also referred to as the volume law. So I'm wondering whether as your y parameter is changing, is there actually a change from area to volume law, or is it always logarithmic with a different offset, like from minus half?
See, Arul, you can, you can quickly see this. You are the one who can easily see this quickly. See, this is the equation of the eigenvalues distribution, right? And as you know that the solution of when this goes to 0, this end left-hand side goes to 0, as I said, y goes to infinity, solution corresponds to this case. Right. Which is the solution of the standard. So y goes to infinity corresponds to, of course, y goes to infinity corresponds to, of course, the ergodic state of Don page entropy. Now, why? Because let's not forget, I did not include here any other real physical constraint except trace rho of is equal to 1. In real physical system, you have to include additional constraints.
Yeah.
Okay. And symmetry is, of course, not affected. Yeah. But that, I think, was already known. Okay. If you do not put any other constraints like conservation of energy or other things, okay. So then it will, of course, grow to the Don page.
No, so my question is whether for small y, it is volume law.
For small y, it is volume law. See, as I said that for small y, I have not studied that, so I cannot say that, because to say that you have to study the system dependence, right?
Yeah, exactly. Yeah.
So, and Devanshu, does not believe in studying system dependence.
No, that would be an interesting thing also for condensed matter kind of system.
Exactly. No, I understand, but I'm sitting in ICTP and he's in IIT Kharagpur, and therefore
I understand, yeah.
we have a very weak entanglement.
So the other one is a comment. I mean, will it be interesting to study a case where C is the diagonal dominant? And then you...
Of course, no. That's the whole purpose of this talk, is to say that all the time we are talking about this this particular case, what I showed, this particular case, right? Stationary Wishart, which leads to stationary Wishart matrix, right. But actually that is a very small set of states.
That's your picture. I'm wondering whether you have a C which is diagonally dominant, whether that...
of course, it will be relevant.
Because there the thing is actually you're starting from a maximally entangled state, and then your y equal to 0 will be a maximally entangled state, unlike these situations, probably.
Exactly. Yeah. Okay. So in that case, now then this equation will change, right?
Yeah.
Because let me say it again. So here, this equation is representing, because this equation corresponds to this ensemble, right? Yeah. And this ensemble, you cannot actually, for maximally entangled state to, as an initial state, you have to really choose H and B. So it will be like we all know, Arul, that in quantum chaotic systems, we have studied the transition from GOE to GUE and that kind of transitions, right? So it will be from one type of ergodicity to another kind of ergodicity.
Right.
Correct? Yeah, so all these are open questions, of course.
Okay, yeah, thanks, Pragya. It's nice to see this.
So are there any more questions? Okay, so if not, let's thank Professor Shukla and also the other speakers in the session, Professor Joe and